A subjective search primer. The cause is hidden, but the result is known. Ovid. Error is the path of truth. Hans Reichenbach. Subjective search combines subjective probability and Bayes' law to find hidden causes when all that can be seen are the effects. It uses multiple observations and deductions to choose the best among a set of options. Selection search chooses among a fixed set of models, and evolution search chooses among a changing set of models. Subjective search provides a foundation for agile practices that could be called subjective software engineering. Basics. Drawing warm water example. Consider drawing warm water to wash your hands. Nobody ever knows exactly where to turn the handles of a faucet to get the desired temperature of water, so everyone uses a familiar search process. First, they guess where to turn the handles and then repeatedly test the temperature and adjust the handles accordingly. Finally, when the water feels close enough to the desired temperature, they stop and wash. Everyone uses interpolation to estimate which direction and how far to turn each handle. When the water feels too cold, they increase the hot water and/or decrease the cold water, and vice versa. When the temperature feels much too hot or much too cold, they turn the handles a lot. When the temperature feels close to what they want, they turn the handles a little. This iterative process of testing and adjusting using interpolation is the essence of subjective search. Each adjustment of the handles is one application of Bayes' law. This process enables everyone to draw whatever temperature water they prefer. Some hidden causes are so simple and intuitive that people search for and find them without even realizing. Young children draw warm water by themselves all the time. The cause is the position of the handles, and the effect is the temperature and flow of the water. Other hidden causes take a lot of disciplined hard work. Writing software is truly difficult. The cause is the source code, and the effect is the behavior of the program. Subjectivity. The word subjective. The many different meanings of the word subjective can cause confusion. In this chapter, we use the word subjective to mean two specific things: observer-based and opinion-based. We use the words observer and opinion to mean one or the other, and we use subjective to mean both. Observer-based. Subjective probabilities are assessments from the point of view of a specific observer, as opposed to assessments derived from the external world independent of observers. Note that observer-based knowledge can be completely objective and that observers usually agree with objective knowledge. Opinion-based. Subjective probabilities can be based on personal opinions and arbitrary rules. Deductions are completely objective when all of the evidence is objective. Deductions are subjective when any of the evidence is based on personal opinions or arbitrary rules. In general, the word Bayesian means the same thing as the word subjective, and the word frequentist means the opposite. Metaphors for personal opinions. Richard Jefferies wrote, "The most important questions in the theory of probability concern ways and means of constructing reasonably satisfactory probability assignments." And, "Your subjective probability is not fetched out of the sky on a whim." Think of drawing warm water. Bet. Some people think of opinion-based probabilities as bets. Emile Borel concluded that individuals can quantify their degree of belief with a bet. The amount he or she is willing to wager shows how much he or she believes. Nate Silver argues that an observer's prior should equal the odds that he or she is willing to bet. Measure of belief or ignorance. Other people think of opinion-based probabilities as measures of certainty or lack thereof. Sharon Birch McGrain wrote that subjective probability is a measure of informed belief. Conversely, David Hand wrote that subjective probability is a measure of ignorance. Placeholder. Yet other people think of opinion-based probabilities as placeholders for objective knowledge. Richard Jefferies wrote, "The chance of H prime is a placeholder for as yet unknown information." Subjective deduction. Absolute probabilities and Bayes' law enable one-step deductions. Absolute probabilities. Binary events. Absolute probabilities concern the odds of individual binary events, such as whether a flipped coin will land heads up and whether a new species will be found within a given area. In software, binary events include whether users will be satisfied with a given dialog as described by a requirement document or implemented by a body of code, or whether a bug lurks within a specific requirement or function. Meanings of absolute probabilities. Observers can use three kinds of evidence as absolute probabilities. Objective samples. An observer can use objective facts when he or she has enough objective samples. Probabilities like 0.7, 0.5, and 0.1 mean that the observer has seen binary events occur at these specific rates. Personal opinions. Richard Jeffries noted that a lot of problems are not about statistics, but about judgments. An observer can use personal opinions when he or she can make educated guesses. Probability is a measure of how much information an observer has about the physical world. The probability 0.5 means that the observer is completely unsure whether a belief is true. Probabilities like 0.7, 0.9, or 0.99 express varying degrees of certainty that a belief is true. Probabilities like 0.3, 0.1, or 0.01 express varying degrees of certainty that a belief is false. Arbitrary rules. An observer can use arbitrary rules when he or she knows nothing, such as presuming that for events with n outcomes, the odds of each outcome are 1 over n. The probability 0.5 means that the observer knows nothing about the odds of a binary event. Also note that statisticians often use the arbitrary numbers 0.95 to represent true and 0.05 to represent false. Bottle cap example. Consider estimating the odds that a flipped bottle cap will land heads up. Objective samples. An observer might actually flip a bottle cap 100 times and see that it lands heads up 16 times, and so he or she might initially guess that the odds are 16 to 84. Personal opinions. An observer who has never flipped a bottle cap yet knows a little physics might guess that the odds lie somewhere between 50-50 and say 10-90, and so he or she might initially guess that the odds are 30-70. Arbitrary rules. An observer who has never seen a bottle cap before and has no idea what will happen might initially guess that the odds are 50-50. Empirical Bayes means as objective as possible and as subjective as necessary. Naturally, everyone should use the best evidence that they can get to guide decisions. They should use objective information whenever possible. Then, they should use effective opinions to fill in gaps. Then, as a last resort, they can use arbitrary rules to fill in any remaining gaps. When people run out of objective information, they can, should, and must fill in with personal opinions and arbitrary rules because there is nothing else to use. Always using the best evidence that one can get is called empirical Bayes. Bayes' law. In decision-making, it is deliberation, not observation, that changes your probabilities. Jeffries. Bayes' law is the equation that shows how to incrementally improve an assessment that a belief is true based on new evidence. Bayes' law, P of B given E equals P of E given B divided by PE times PB. In this equation, B is a belief, E is some new evidence. P of B is the observer's initial assessment, or probability, that belief B is true. P of B given E is the observer's updated assessment, or probability, that belief B is true, given the new evidence E. And P of E given B divided by PE is an update function that uses interpolation. Probabilities before the computation, like PB, are called priors. Probabilities after the computation, like P of B given E, are called posteriors. Update functions are called likelihoods. Interpolation. The update function shows how much to change assessment PB based on how close the evidence E comes to what the observer expected. Knows little. When the observer knows little about the probabilities of either E or E given B, then he or she learns little. In symbols, when the observer knows little, then the probability of E given B is around 0.5, and the probability of E is around 0.5. And so the update function, the probability of E given B divided by the probability of E, is approximately 1, and nothing will change. So the probability of B given E approximately equals the probability of B. This happens when the observer sees a truly new phenomenon and has no idea what to think about it. Learns little. When the probability of the evidence E is the same whether or not an observer believes B, then he or she learns little. In symbols, when the observer learns little, then the probability of E given B approximately equals the probability of E. And so the update function approximately equals 1 and nothing will change. This happens when the observer repeats an experiment and learns nothing new. This happens when the observer moves the handles on the sink, but the temperature of the water still feels the same. Learns a lot. On the other hand, when the observer knows something about the probabilities of E given B and the probability of E, and they differ from each other, then he or she will learn a lot. The difference reveals both a potential error in what is currently known and an opportunity for learning. One-step deduction. Bayes' law shows how to reassess the odds of a specific belief given new evidence using one deduction. Before electronic computers, when computations were made by hand, one deduction is all anyone ever wanted to do. Many books and essays about Bayesian statistics emphasize these one-step deductions. Beach example. On a beach, 10% of the kids are visitors, 90% of the kids are locals, all visitors swim, 60% of locals swim, and 40% of locals surf. You just saw a kid swim. What are the odds that the kid is a local? First, we need to know the odds that any kid swims, which is the weighted average that visitors and locals each swim, which is 0.64. Then Bayes' law can answer the question directly, going from probability of local to probability of local given swim. This is equal to probability of swim given local divided by probability of swim times probability of local, which equals 0.84. The exact answers to problems like this can be computed in one deduction. The odds in this example are completely objective. Subjective search. Relative probabilities and sequential analysis enable selection and evolution search. Relative probabilities and area events. Relative probabilities contrast the odds of multiple models within a set. A coin could be represented by two models, heads and tails. A die could be represented by 6 models, one for each face. When choosing which tasks to implement in the next iteration, each task could be represented by its own priority. When implementing a feature or fixing a bug, each possible set of code changes could be represented by its own model. Meaning of relative probabilities. When comparing n models, the probability 1 over n means that all outcomes are known to be equally likely, that they are believed to be equally likely, or that nothing is known about them. For example, the odds that each face of a fair coin will appear is 1/2, and the odds that each face of a fair die will appear is 1 over 6. The probabilities differ when one model is more likely than another. Note that the probabilities associated with each model can embody objective data, personal opinions, and arbitrary rules. The probabilities of all models often sum to 1.0, but they don't need to. Models can sum to any value as long as the observer updates the probabilities of all models consistently. For a fair die, an observer could assign each face a probability of 0.5, which would sum to 3.0. For a bottle cap, an observer could assign probability of heads equals 0.1 and probability of tails equals 0.3, which would sum to 0.4. When modeling task priorities, a backlog could have 3 tasks marked urgent or 0.99, and the sum of all priorities would be much larger than 1.0. The probabilities of models need not even remain within the range of 0 to 1. Rounding errors and quirks in computations can easily cause the sum of all probabilities to drift above 1.0. After every experiment, an observer could renormalize the probabilities so that they all sum to 1.0, but that does not always make sense. For example, when the probabilities represent priorities, renormalizing makes no sense. Absolute and relative probabilities should only be mixed with care. To convert relative probabilities to absolute probabilities, perhaps they should be renormalized so that the sum equals 1.0. To convert the other way, perhaps they should be denormalized. Always choose the best model. As a rule, when choosing among models, observers should always choose the one with the highest probability. Jerzy Neyman and Egon Pearson argued that the only correct reason for rejecting a statistical hypothesis was to accept a more probable one. For example, if an observer must choose among 3 options and he or she believes that the probabilities are A is 0.65, B is 0.64, and C is 0.52, then he or she should choose A because it is most likely right, if only by a little bit. Murky decisions. Observers often struggle to articulate and formalize everything that they know about their decisions. Observers may choose models with lower probabilities for intuitive reasons that are not expressed in the model and that they cannot otherwise articulate. For example, an observer could choose models B or C above for reasons that he or she cannot explain. One well-known heuristic states that observers can be certain that one model is correct when it is 3 times more likely than all others, though many searches never achieve such certainty. Sequential analysis. Big endeavors are often carried out through a series of many small steps because people can only do a small amount of work at a time, and because experiments often reveal only a small amount of information at a time. Many real-world subjective search problems require tens or hundreds or thousands of experiments to solve, or more. For these problems, subjective deductions compute trends rather than direct results, which is called sequential analysis. Bayesian models resemble infinite impulse response filters. As observers gather more data and more becomes known, assessments should improve and the error should go towards zero. Selection search. Selection search is a statistical process for shopping or choosing among a relatively small and fixed set of models. After each experiment in a series, the observer improves the probability of each model. The results are probability distributions. Hidden billiard ball example. For some problems, the models are essentially alike. In his original thought experiment, Thomas Bayes wanted to find the location of a hidden, randomly placed billiard ball. Bayes divided the billiard table into a fixed grid of n identical segments. Each grid segment is one model. The table shows this process. Priors. Arbitrary rule. To start, Bayes presumed that the original ball had a 1 over n probability of lying within each segment. In Table 1, the observer divides the billiard table into 8 equal segments and initially guesses that the odds that the hidden ball lies within each segment are 1 over 8. Personal opinion. If the observer had other beliefs, for example, if the observer believed that the table were not level, he or she could assign different priors to each segment as appropriate. Experiment. Then Bayes performed a series of experiments to improve the estimate. During each experiment, Bayes rolled another billiard ball randomly onto the table and determined whether it stopped to the left or right of the hidden ball. After each experiment, he updated the probability that the hidden ball lies within each segment using his law. The probability in this segment given the result equals the probability of the result given in this segment divided by the probability of the result times the probability in this segment. The values for probability of result in this segment are shown in the last 2 rows of Table 1. After the first and second experiments, segment 5 does not look correct. After the third experiment, segment 5 could be correct. After 60 experiments, segment 5 stands out as obviously correct. Note that the priors use arbitrary rules and the experiments produce objective data. Also note that after the second experiment, the models do not sum to 1.0 and that the probabilities of some models exceed 1.0. Most important task example. For some problems, the models differ significantly. A backlog might contain 5 tasks: refactor a class, improve the performance of search, add a new dialog, change the query logic, and update the legal boilerplate. Keiko is asked to prioritize the tasks in the backlog because she only has time to implement one before the next release. Table 2 shows her process. Priors. Arbitrary rule. If Keiko knows little, for example, if she is a new hire and has never met the client before, she could presume that all tasks are alike and initially give each task a priority of 1 over n or 0.2. Personal opinion. If Keiko knows more, for example, if she has worked with this client before, she should give each task a different priority based on her experiences. If Keiko believes that the client prefers big and visible, she might assign the priors as follows. Refactoring a class gets 0.1 because it is invisible. Improving the search performance gets 0.2 because it makes no functional difference. Adding a new dialog gets 0.3. Changing the logic of a query gets 0.3. And updating the legal boilerplate gets 0.1 because most users don't care. In this case, Keiko has opinions. Experiments. From there, Keiko can perform experiments by asking other stakeholders for their thoughts. Tariq. Keiko asks Tariq, the programmer who last maintained the program. Tariq notes that both the performance and dialogue tasks need the refactoring task first. So Keiko multiplies the priorities of refactoring by 3 to make it equal to the highest priority, and the performance and new dialogue tasks by 0.6. Emily. Keiko talks with Emily, who worked on the first version of the program and who remarks that the client recently got sued. So Keiko multiplies the probability of the boilerplate task by 2.0 and all other tasks by 0.89. Sanjay. Keiko talks with Sanjay, who works in the legal department, and who says that the lawyers are still rewriting the fine print. Keiko should hold off on that for now, but he really wants the new queries. So Keiko multiplies the priorities of the boilerplate by 0.75 and the query logic by 1.2. Now the query logic has the highest priority, 0.32, though not by much. Keiko used opinion-based priors and 3 different opinion-based bits of evidence. If Keiko could have determined objective probabilities, she would have used them. But here she couldn't. Keiko used her best guess numbers. Note that polling can give similar answers to subjective search, but subjective search also allows observers to value each bit of evidence differently. For example, when the observer has more confidence in one stakeholder's opinion than in another, or when the observer compensates for known biases. Also note that within the limits of rounding, the probabilities of all models sum to 0.1. Evolution search. One might aspire to consider and track all possible models, but that can become overwhelming. Tracking tens of models is easy, tracking hundreds of models is possible, yet tracking thousands of models is simply impossible. Nobody wants to feel overwhelmed. Nobody wants to waste their efforts by evaluating a lot of low probability models. In particular, combinatorial problems have too many models for anyone to track them all explicitly. Prototype evolution. When too many possible models exist, observers commonly start with one working prototype and then incrementally improve it. When the observer realizes that the current prototype is not good enough, he or she looks for a better, if previously unconsidered prototype and swaps it for the current one. The observer considers and makes small changes incrementally, one at a time. At each step, he or she explores the adjacent possible and then continues using the best improvement. The results are exemplars in the neighborhood of local maxima or samples from probability distributions. Evolution search is a statistical meta-process for designing or creating new models. Evolution search deals with problems in models by improving the probabilities of the models and then improving the models themselves. In artificial intelligence and numerical analysis, prototype evolution is called hill climbing, and observers generally strive to make the biggest improvement possible at each step. Dialogue design example. Consider a dialogue with some controls to select and modify information, and a table to display the results. If an analyst limits the models to whether to rename each control, then the number of models to consider is exponential in the number of controls. Since each control can change in many different ways, order, position, name, style, graphics, functionality, and so on, and since each control can be added, deleted, the number of potential changes to consider is very exponential. Humans cannot explicitly consider all possible changes to small dialogues, say 8 controls. Computers cannot explicitly consider all possible changes to medium-sized dialogues, say 16 controls. Priors. The users start by making their best guesses for the initial requirements. The analysts and programmers start by implementing the core features that users asked for. The resulting dialogue is a working prototype. Experiments. After each sprint, the analysts and programmers demo their current working prototype to a group of users for feedback. When the analysts and programmers worked hard and implemented all the features that the users asked for, they will expect that the users will be pleased. The users may respond, "That's cool." The more the users like the demo, the more the analysts and programmers will raise their estimate that the current prototype is good enough. At some point, the analysts and programmers will conclude that they are finished and will move on to implement the next feature. The users may also respond, "That's lame." The more the users dislike the demo, the more the analysts and programmers will feel crushed. Then they will look for a small set of improvements to make. Thousands of potential changes exist, as hinted at in Table 3. All of them take work to implement and potentially add noise for users, so nobody should implement any of them without good reason. Before the demo, the analysts and programmers gave little thought to these other changes because they were considered either unnecessary or wrong. The analysts and programmers continue this process until the users either become satisfied or the resources run out. Some of the many possible changes to a dialog. Add autocomplete to fill in fields automatically, make the dialog prettier, add columns to or remove columns from the table, add filters and sorts when queries return too many records, segmentation to segment the data, add links to social media pages related to the results, enable editing individual records, enable editing many records at the same time, allow different users to access different records, add links to drill into any value in the table, show the history of the changes to any given record, allow each user to add or remove columns for their own views, add bookmarks that will return the exact same results in the future, allow users to download data in Excel or other formats, email the results to a client, or represent numbers as graphs or colors or icons. When an experiment fails, in general, analysts and programmers use evolution search intuitively without numbers. Here, we assign arbitrary numbers to show how it works. Some analysts and programmers work on a new dialog. They finish all of the initially requested features and believe that their implementation will make the users happy. So before the demo, the probability of happy with dialog is 0.95. When the analysts and programmers realize that the current dialog doesn't work well enough, they estimate how disappointed or annoyed the users are and adjust accordingly. For example, the users may demand autocomplete or that the dialog be prettier. Say that the analysts and programmers are only 1/4 as confident in the working prototype as before. So the probability of happy with dialog given the demo equals 0.25 times 0.95, which equals 0.24. It may take a while to fix the dialog, and users might even learn to like it. Regardless, everyone expects the worst, and so analysts and programmers will find a new model that should work better and modify the dialog to match. Autocomplete. Say all of the users vote for adding autocomplete. Before the demo, the analysts and programmers had thought that autocomplete was unnecessary, so p happy with dialog plus autocomplete equals 0.5. Say that after the demo, they are 10 times more sure of this theory than before, so probability of happy with dialog plus autocomplete given the demo is 10 times 0.05, which equals 0.5. When users complain about one detail, they will often complain about other details later, but autocomplete heads in the right direction for now. Pretty. Say 2/3 of the users vote to make the dialog prettier. Before the demo, the analysts and programmers had thought that pretty was unnecessary, so the probability of happy with dialog plus pretty was 0.5. Say that after the demo, they are 6.7 times more sure of this theory than before, so the probability of happy with dialog plus pretty given the demo is 6.7 times 0.05, which equals 0.34. Maybe they don't know how pretty to make the dialog. When users wanted a little prettier, the team might assign a programmer to add some clip art. When users wanted a lot prettier, the team might hire a graphic designer. After deliberation, the analysts and programmers are much surer of the dialog with autocomplete than of the original dialog or the dialog with pretty. So they will add autocomplete before the next demo. Problems with evolution search. Experience has revealed a number of problems with evolution search. Local maximum. At discontinuities, models cannot improve easily. When a prototype gets to a local maximum, it may take a radical change, such as a massive redesign of a GUI or a refactor of an architecture to continue improving incrementally. Plateaus. On plateaus, improvements are unclear. Plateaus occur when users don't know what they want and when programmers don't know how to reproduce a bug. All efforts may seem like aimless wandering. Slow. Progress can be slower than anyone likes. Finding effective solutions can take many more rounds of refinement than desired. Horizon effect. The horizon effect means that people may not be able to predict how the results will turn out. Dramatic surprises can arise continually and annoyingly. Focus on the product. Chip Conley noted that the design process tends to focus on the product rather than on the customer, on the features of the program rather than on how best to help the client. This distinction relates to the difference between the bottom and middle levels of Maslow's hierarchy. The bottom levels concern the user's functional needs, and the middle levels concern their emotional needs. Strengths and weakness. Subjective search is both tremendously useful and enormously problematic. The strengths include that it sheds light on the ways that brains work and that deviations explain many biases and errors in human reasoning. The weaknesses include that results can have significant errors and that many problems are not Bayesian. Insights into how brains work. Expertise is subjective. Observers always have opinions. All analysts and programmers bring their own knowledge, experiences, trainings, facts, hopes, fears, purposes, and delusions to every project that they work on. In crime shows like Bones or CSI, characters occasionally argue that everyone should avoid preconceived notions about evidence. They are dead wrong. People's immediate environments inundate them with so much information that they need models and expectations to filter most of it out and to help them make sense of the rest. Catherine Schultz writes, "Perception is interpretation of sensation." David De Silva writes, "Pre-established schemata guide our attention to evaluate new information." Tom Kelly writes, "You have to interpret or intuit shades of meaning to derive underlying motivations or needs." Preconceived subjective notions enable everyone to find, understand, and use information. Only young children actually believe what they see and have few preconceived notions, which is called naive realism. But they are unaware of the dangers of street traffic and are easily distracted by toys and candy. One would never ask small children to evaluate crime evidence or design sophisticated software. All expertise is based on preconceived notions and subjective points of view. Gains and loss are asymmetric. Becoming more certain and becoming less certain are asymmetric. Psychologists have shown that people gain confidence much more slowly than they lose it. When an observer starts out certain, 0.95, and loses half his or her certainty, the result is 0.48, the loss is significant. When an observer starts out skeptical, 0.05, and becomes twice as sure, 2 times 0.05 equals 0.1. The gain is incremental. This difference may help to explain why people worry so much more about loss than about gain. Insights into human error and bias. Many deviations from subjective search correspond to specific human biases and error. Deny personal bias. Nobody can avoid personal bias, and those who don't acknowledge their biases will succumb. The only alternatives to acknowledging personal biases are wishful thinking and naive hope. Unfortunately, everyone fools themselves. People believe that they know more than they actually do. People believe that they are more impartial than they actually are. People have systemic biases, but those who are aware can try to compensate. Nate Silver notes that with Bayes, people must choose a prior, so they cannot pretend that they have no biases. Subjective priors acknowledge that people perceive reality through subjective mental filters. Prefer optimism over realism. When given options, many people will assign probabilities based on what they want to happen rather than on what they expect to happen. Unfortunately, few people can control their circumstances. Fred Brooks' calling the shot is a useful prior because people should state clearly what they want. But it is also problematic because it can set up unrealistic expectations. Projects always change in unexpected ways. People should deal with their actual situations rather than their preferred situations, even though hope springs eternal. Prefer changing probabilities over changing model. People can refuse to change their mental models and stubbornly only improve the probabilities of their existing models. This can be seen as the difference between selection search and evolution search. Cranky old men who argue that, in my day, we listened to Elvis and the Beatles, and we liked it, kids these days in their rap, remain stuck in the past. Anyone who insists on following a flawed plan remains stuck in the past. Prefer facts over probabilities. People are not statisticians. Nobody cares about the probabilities of binary events. Nobody wants to evaluate the probabilities of many different decisions or plans. They really just want to make one effective decision or plan. So humans often treat opinions and judgments as facts. They take the highest probability model as a guaranteed success. Consider a case where the probability of A is zero point 0.6 and the probability of B is zero point 0.4. Most people leap directly to A is a sure thing. Everyone converts estimates into promises. They just do. Discoveries for requirements and architectures become facts rather than possibilities. The best decisions can still be very wrong. Unfortunately, subjective search doesn't give anyone the warm, fuzzy feeling of certainty. Subjective choices often contain errors, and assuredly some of them will be wrong. The best subjective decisions are not right, but are less wrong, and unfortunately can even be arbitrarily wrong. Planning helps to answer questions like, given what we know and ignoring what we don't know, what's the best answer? And given the stated requirements and ignoring the requirements that are missing, misunderstood, or wrong, what is the best architecture? But the answers may be neither very good nor good enough. Until all details become known, then at least some of the details will remain unknown, and only heaven knows how much pain they will cause. Flipping around the logic for why everyone should choose the highest probability models shows why they should also beware that model. When choosing among options where the probability of A is 0.65 and the probability of B is 0.64 and the probability of C is 0.52, A is the best decision, though it remains far from certain. The observer also knows that there is a 0.35 chance that A is wrong. One could argue that 0.5 of A is wrong, although such an argument would be incorrect. Consider the 20 doors metaphor from security. Locking 19 of 20 doors does not make a building 95% secure. Option A could still be horrible. Note that when predicting the future, all other decision processes can also be horribly wrong. Many decisions are not Bayesian. In the broad spectrum of problems, some are Bayesian and others are not. Some problems can easily be solved by subjective search. Historically, Bayesian researchers emphasized one-step deductions and selection search. Evolution search is a much more recent technique adapted from computing. Bernoulli. A lot of early research into Bayes, and especially Bayes' original essay, focused on Bernoulli trials. Bernoulli trials are binary events where each example is independent and has a fixed probability, such as flipping coins, throwing dice, or rolling billiard balls. Exchangeable and partially exchangeable. More recently, Bayesian research has focused on exchangeable and partially exchangeable events. Jeffrey notes that events are exchangeable when only the ratio of true to false matters and not the order, such as when drawing colored balls from an urn. Bruno Di Finetti linked exchangeable and subjective search in 1931. Jeffries explains, exchangeability undoes the dreaded combinatorial explosion. Partially exchangeable events have Markov dependencies, such as in Markov chain Monte Carlo techniques. Smooth combinatorial. Evolution search can solve a wide variety of combinatorial problems, specifically ones that have smooth gradients, where discontinuities are smaller than step sizes, and affordable paths, where the total steps fit within budgets. Other problems are not Bayesian. Unfortunately, other problems cannot be solved using subjective search. Undecidable. Gödel's incompleteness theorem shows some strict limits on what can be known. Undecidable problems, such as the halting problem, cannot be solved by any means in general. Intractable. Answers to intractable problems like satisfiability and factoring large numbers are easy to verify even though they remain difficult to find. Exponential and super-exponential problems cannot be solved by any means in any reasonable amount of time. Hyperbolic, chaotic, and fractal. The central limit theorem assumes a linear distribution with smoothness so that interpolation works. However, fractal, power law, chaotic, and Pareto properties can have jagged or infinite paths for which interpolation is impossible. Nash equilibria. Jeffries states that Bayes does not help with Nash equilibria, such as the prisoner's dilemma, where information outside of the system, such as how an opponent will behave, affects the answer. Note that all programs can be interpreted as Nash equilibria in games between users and programmers. Magical unknowns. Some problems require magical knowledge, such as passwords or lottery numbers. Magical unknowns can only be solved by sharing or discovering otherwise secret or random information. One of the hardest bugs to solve that we know of involved realizing that an API for detaching processes from the UI existed and that it would help. It was buried deeply within MSDN and was stumbled over only by accident. Magical knowledge often creates job security for experts. Unknown unknowns. In many cases, users know neither what they want nor how to get it. We have seen both users and developers say, "This doesn't seem right, but I don't know what to do about it." Or, "I can't describe it, but I'll know it when I see it," also called icky-wissy. When the effects are unknown, then the hidden causes are buried one layer deeper. However, subjective search can still help to solve or approximate many instances of these problems. For example, Alan Turing used subjective search to guide code-breaking efforts back when cryptography was still fairly weak. In Nash equilibria, subjective search may not be able to create strategies such as tit for tat, though subjective search can often help to choose which known strategy to apply. Subjective software engineering. Subjective search provides a solid foundation for agile practices because it is incremental and tolerates uncertainty. Subjective search applies to everyone in requirements in software engineering. However, we mostly leave the applications to architects, testers, and managers as exercises for readers. Analysts and programmers. Most analysts and programmers using agile processes in real software projects do subjective search anyways, if informally, ad hocly, inconsistently, and with varying degrees of awareness. Clearly, analysts and programmers make informal decisions based on incomplete information all day long. We suspect that analysts and programmers have ignored subjective search mainly because it is so obvious. Analysts, priors. First, analysts should presume that users know what they want. They should document what users say literally, even if, as the Oatmeal complained, they say, quote, "We want an edgy website that pops," which nobody knows how to make. Second, analysts should fill in as many of the remaining details as they can using their best guesses based on their training, experiences, opinions, hopes, desperations, delusions, and so on. Third, analysts should fill in as many of the remaining details as they can using arbitrary rules defined by conventions and standards. Experiments. Then analysts should repeatedly run experiments, questioning everything, user, analyst, and programmer input alike, and adapt as they learn. They should repeatedly ask, what do users really need as individuals and as groups? They should repeatedly show users the requirement documents, paper mock-ups, working prototypes, and other applications. During each demo, they should ask for feedback and watch how users respond, seeking out missing, wrong, and ambiguous requirements. Analysts should use their responses as new evidence to improve their requirements. Programmers, priors. First, programmers should start each project with either an existing codebase or an empty codebase. Experiments. Then programmers should repeatedly run experiments to implement features and fix bugs. They should make their best guesses to improve the source code, make that improvement, and then assess the results. A programmer might show the code to some colleagues for review or demo the prototype to some testers or users to see how they respond. When a code change implements a feature, fixes a bug, or cleans up the code well enough, the programmer should commit the results and move on to the next task. If not, the programmer should undo the change and try his or her next best guess. Some features and bugs have been seen thousands of times before, and programmers know exactly what code to write. Some features and bugs are unique to their experience, and programmers must track down the lines of code doggedly, using guesswork and trial and error. And some features and bugs are beyond their understanding, such as satisfiability or Heisenbugs, and they must wait until someone provides more information. Both selection and evolution search. Everyone shifts back and forth flexibly between selection and evolution search. Analysts. Analysts routinely use selection search when they prioritize the tasks within backlogs. Analysts also routinely use evolution search to refine, split, merge, add, or delete individual tasks. Programmers. Programmers primarily use evolution search to create codes. The number of possible source codes is exponential in the number of tokens, so nobody can keep track of all possible solutions to new features and fixed bugs. Source codes are in general so large that developers can only make small changes to them at a time anyways. Programmers also use selection search to fix bugs when multiple possibilities exist and they are uncertain about which solutions will work. Programmers may also use selection search to develop several different prototypes of a feature at the same time. They can use the single best prototype as the final version, or they can merge the best elements of each into the final version. Researchers. In Learning Through Application, The Maturing of QIP in the SEL, Vic Basili writes like a Bayesian, quote, "The insights gained from pre-experimental designs and quasi-experiments became critical, and we combined them with what we learned from the controlled experiments and case studies. The experience factory requires the use of insights and intelligent judgment based upon observation for the application of ideas, concepts, and processes." And, quote, "Informal feedback also, and perhaps surprisingly, provided the major insights." It's not a surprise to us. If subjective search works for researchers at NASA, it should work for practicing analysts and programmers too. Note that Basili's arguments that research judgments are subjective totally contradict his frequentist ideals for GQM. He can't have it both ways, but he could become an empirical Bayesian. Scientific process. Enrico Fermi and Richard Feynman showed that, quote, "Bayes' law lies at the heart of the scientific process." Leonard Savage wrote, quote, "When we have little data, scientists disagree and are subjectivists. When they have piles of data, they agree and become objectivists." Dennis Lindley wrote, "That's the way science is done." Subjective search is the only solution. We believe that only the deliberate discovery and refinement processes guided by subjective search lead to effective requirements and source codes. We do not know of any other effective approaches, all of the rhetoric about planning and architecture and project management notwithstanding. We believe that software that cannot be written using subjective search cannot be written at all. When objective information runs out, people must guess or make subjective decisions. David Friedman wrote, "Look over the evidence, weigh the biases, consider the qualifications and limitations, and take your best shot at deciding. No expert could do better. Taking one's best guess and following up on it is not hacking. Doing anything else is." Culture wars. Statisticians have engaged in deeply entrenched culture wars over the years. Frequentist versus Bayesian statistics. Statistics spans a vast spectrum. Table 4 contrasts the two extremes. Essence. Here are three significant points on the spectrum of statistics. Frequentist. Quote, "Probability is the proportion of times an event occurs in an infinitely long series of trials." Quote, "It is a property of the external world." Frequentists believe that probabilities are objective measures of the world. They reject both observer-based and opinion-based probabilities. Half-Bayesian. Half-Bayesians generally accept observer-based and reject opinion-based probabilities. Judea Pearl argued that Bayes' original thought experiment to find the location of a hidden ball would satisfy most frequentists, and that most Bayesian literature concerns topics like influence graphs and causality, with which frequentists have little problem. Bayesian. Bayesians generally accept both observer-based and opinion-based probabilities. Context. Lots of data, the past. Frequentist statistics requires a lot of existing objective data which comes from the past. When insufficient data exists, frequentists can only twiddle their thumbs. Little data, the future. When little existing objective data exists, especially when predicting the future, Bayesians make best guess subjective decisions and proceed. Basis for comparison. When lots of data exists, Bayesian and frequentists usually agree with each other. However, Bayesians and frequentists can also use the same data and make different decisions. Minimize maximum loss. Frequentists generally compare models by minimizing maximum loss, known as minimax. This makes sense when deciders get only one chance, such as when projects near deadlines and deciders only have resources for one attempt. Minimize expected loss. Bayesians generally compare models by minimizing expected loss. This makes sense when deciders get many chances, such as when projects have distant deadlines and deciders have multiple opportunities to fix problems later. Software examples. Algorithms. Algorithms are objective properties of the universe that exist independently of observers. Algorithms for sort and Fourier transform were used centuries before electronic computers existed. Programs. All requirements and lines of code are observer-based because only analysts and programmers write them down. The universe does not cause them. The universe would be equally happy with anything. All requirements and lines of code are properties or opinions of people because they contain elements of someone's belief that a given requirement describes or a given line of code implements what the user wants. 50 years ago, nobody wanted any of the requirements or lines of code for Microsoft Office or Facebook. 50 years from now, they may want something else entirely. Culture wars. What's the collective noun for a group of statisticians? A quarrel. Statisticians have fought philosophical battles that would put Lilliputians to shame. Frequentists have many criticisms of Bayesians. Bayesians have just as many responses and counter-criticisms. Battles between Bayesians and frequentists raged throughout the 1900s, though over the past few decades they seem to have come to a truce. Frequentist criticisms of Bayes. Some statisticians, including Ronald Fisher, who developed frequentism, reject subjective approaches outright, or at least give subjectivity as wide a berth as possible. Other statisticians, including Pierre-Simon Laplace and Judea Pearl, switched, at least in part, from Bayesianism to frequentism for the following reasons and others. Other statisticians ambivalently state, quote, Bayes' rule is wrong, except for the fact that it works. Or they complain that the fundamental vulnerability of Bayes is that, quote, its magical powers depend on the validity of its probabilistic inputs. Personal opinions are not objective. One definition of empirical Bayes is, quote, be as objective as you can be and as subjective as you must be. Personal opinions should be avoided. Arbitrary rules are not objective. Ronald Fisher argued, thinking that you don't know and thinking that the probabilities of all possibilities are equal is not the same thing. Arbitrary rules like 1 over n should be avoided. Priors are not objective. Ronald Fisher argued that stating a prior contradicts objective science. Small samples are not objective. In general, applying Bayes' law many times based on many experiments leads to more truth, and applying Bayes' law fewer times based on fewer experiments leads to less truth. This implies that fewer experiments should be avoided. In the task priority example above, Keiko ran 3 experiments, which is far too few for any meaningful frequentist poll. Not use much. A recent survey of working statisticians found that few of them actually use subjective probability on the job. In the textbook Doing Bayesian Data Analysis, John Kruschke barely even mentions subjectivity. Empirically, many statisticians avoid subjectivity. If only ad hoc decision makers actually use subjectivity, then it isn't statistics. Bayesian responses and counter-criticisms. Bayesians generally agree that the criticisms above contain elements of truth, but also argue that they miss the point. In addition, they argue that frequentism has similar problems or worse. They even argue that all frequentist models are subjective, and so frequentist statistics is actually a special case of Bayesian statistics. All models use implicit priors. Bayesians believe that frequentists implicitly use uniform priors, arbitrary rules like 1 over n, in all of their models, despite their denials. Choices of model are subjective. Bayesians believe that frequentism is not actually objective. The choice of any frequentist model lies outside of the data and therefore is a subjective decision. For example, suppose a frequentist wants to describe a typical member of a set, such as the height or income of a group of people. He or she could use the mean, the median, the geometric mean, the harmonic mean, or many other models. The choice of model is subjective and can profoundly affect the results. Sampling errors versus model errors. Sampling errors are well defined with frequentist confidence intervals, but model errors can be far larger. Subjective searches are the only techniques that encourage statisticians to routinely reconsider models, which frequentists never need do. Different units. David Hand notes that subjective and objective probabilities use the same mathematics. Utility, which is probability times value, also uses the same mathematics. Ian Hacking noted that the difference between the kinds of probability are like the differences between weights and mass, which most people cannot tell apart. When the math is the same, units may not matter. Consider that scrambled eggs may combine 3 eggs, 1/4 cup chopped onions, 2 grams salt, and a 1/4 ounce of butter, all of which have different units. Coping. Bayesians strive to wring as much information from each observation and deduction as possible, regardless of what the evidence is. Frequentists resemble snobby programmers who refuse to work on any project with less than perfect requirements. Path toward truth. Bayesians argue that subjective probabilities are not meaningless, they are steps on the path toward truth. Bayesians take personal opinions and small samples seriously because they are approximations of greater truths that can be used now. Sharon Birch McGrain wrote, quote, "Probability is a measure of belief that can escape from repetition to uniqueness." In the task priority example, Keiko needs a philosophy like subjective search to take small samples seriously. Design versus statistics. All of these criticisms highlight a key difference between design and statistics. Designers have relatively small amounts of objective data and make lots of informal ad hoc subjective decisions. Only those who have lots of concrete data and want more formal decisions bother to call in professional statisticians. As decision makers acquire more data, they drift toward frequentism. But those who make lots of informal decisions, such as how to prioritize features or how to write lines of code, don't bother with frequentist statistics. Odds and ends. Tomes have been written about Bayesian statistics, but we will stop soon. Notes. Inverse deduction. The term inverse deduction is the historical term for subjective search. It refers to reasoning from effect to cause or transmuting unknown causes into known causes. Richard Jeffries notes that an observer can update the probability of a belief by either adding or multiplying a reasonable number. Moving targets. Claude Shannon noted that Bayes' law can follow a signal that changes. The probability of finding a bug in a function will change as the function is maintained, and subjective search will adapt. Users can change their minds about the goals or requirements of a project, and subjective search will adapt. Informal reasoning. Richard Jeffries argues that Bayes provides a formal basis for informal reasoning. Bayes merely formalizes what people do naturally anyways. Bayes is, quote, "a logic for reasoning about the broad spectrum of life that lies in the gray areas between absolute truth and total uncertainty." Quote, "We can learn from missing and inadequate data, from approximations, and from ignorance." Rationality. Bayes provides a formal basis for rationality. Leonard Savage argued that, quote, "rational people make subjective choices to minimize expected loss." Or in positive terms, rational people should always maximize expected gain based on their best guesses. We don't know of any better way to make uncertain decisions. Unfortunately, psychologists have shown that people are not rational, so Savage's ideal can only partially work. Even so, rationality remains an important ideal. Notations. Notations about probability tend to drive programmers crazy. Programmers tend to idealize strict functions and strong types. Unfortunately, the p left parenthesis right parenthesis notation is not a function. The vertical bar is not an operator, and the types of the priors b and the posterior b given e may or may not be the same. These notations drive us, the authors, crazy too. History of Bayes. Subjective search has been used for eons in both statistics and computing. History of Bayes and probability. Jacob Bernoulli wrote about subjective probability around 300 years ago. Thomas Bayes, Richard Price, and Pierre-Simon Laplace addressed hidden causes and predicting the future 200 to 270 years ago. Bayes defined his law operationally, so nobody knows whether he actually would have accepted opinion-based evidence. In other words, nobody knows whether Thomas Bayes would actually have been a Bayesian. Pretty funny. Richard Price thought that Bayes' law was so powerful that it could prove the existence of God. Pierre-Simon Laplace wrote that Bayes is, quote, "the primary method for researching unknown or complicated causes." Bruno Di Finetti, Dennis Lindley, and James Berger linked opinion-based decisions with Bayes more than 50 years ago. History of Bayes in computing. Bayesian techniques have been used to make decisions in computing and related fields from the earliest days. Alan Turing. During World War II, Alan Turing used Bayesian techniques to decide which messages cryptanalysts should actually attempt to decipher on machines. He started by arbitrarily presuming that the odds that a particular setting would decrypt a message were 50-50. Analysts then repeatedly gathered evidence to refine the estimate. For example, observing a certain pattern in a ciphertext might suggest that a particular key would work, so the odds for that key would be scaled by an appropriate amount, such as 1.01 or 1.1. Once the odds became 50 to 1, p equals 0.98, cryptanalysts would attempt decryption using that particular key on an actual machine. Using logarithms simplified the calculations. This process reduced the thousands to billions of possible settings to as few as 18. Claude Shannon. At the dawn of the computing era, Claude Shannon used Bayesian techniques to define both information theory and secrecy. Quote, "If the posterior is quite different from the prior, something has been learned. Otherwise, the information content is very low." Judea Pearl. Judea Pearl applied Bayes to artificial intelligence in probabilistic reasoning with intelligent systems. Database analysis. Many researchers and companies have applied Bayesian techniques to mining databases. Image processing. Markov chain Monte Carlo techniques work well for image processing.